So we're going to continue from where we stopped in the last class. So the essence of all this is we should just try and make time to watch these videos carefully, because you have to get an understanding of all these things. So just give it all your best. Now I think you still have some weeks, I mean maybe 4 weeks. So please just try and cool down with it, and follow through, and also read the slides. Go through the slides. You should understand them properly. That's the best for you, because you're going to definitely make use of the concepts at the higher level. They're going to be making references to the things you have learned in this course, definitely at the higher level. So it's just good that you understand them now. Of course, I'm going to provide solutions to the questions you sent to me, but I would not want you to just do the solution, because in the exam it might not be the same thing. It might be something entirely different. It definitely will be something entirely different. So the only way out is you should just understand everything, like understand what they actually mean. Okay, so you did not send me any questions as per the concept discussed in the last class, so I assume that you actually understood them perfectly. I mean, you understood all that was discussed in the last class. So I'm going to take it on from there. So we're going to quickly look at the questions I gave in the last class, so that you will see that up. Okay, so look at this first part. We said we have a relation F equal to from Newton's law of universal gravitation. We said F is equal to G m1 m2 all over r square, where m1 m2 are masses and r is the distance between their centers. That is Newton's universal law of gravitation, which you are definitely still going to come across in this course, is that if for any two bodies in the universe there's a force of attraction between them, that is, this is attracted to this just as this is attracted to this. So if this is m1, this is m2. Okay, so and this is going to be the distance between their centers. So we say this is r. Alright, so we want to get the dimension of this constant g. Okay, this constant g stems from proportionality. If we say F is proportional to the product of the masses, that means F is proportional to the product of m1, m2, and inversely proportional to the square of their distance apart. So their distance apart is r, so it's inversely proportional to r. So it is on dealing with this that we now introduce a constant of proportionality, which we call the Newton's law of universal gravitational constant. Okay, so that's the universal gravitational constant. Alright, so the next thing is we actually want to get the dimension of this g. That means we want to write g in terms of the fundamental dimensions or fundamental units and fundamental parameters that we already know. Okay, so that's what we want to do now. Let's quickly look at it. So we're going to have something like this. So if you have something like this, since you are interested in the dimension of g, the first thing is to make g the subject of the formula. So you can do that by cross multiplying. I believe you should still remember this if you did mathematics. So when you cross multiply this, you're going to have f r squared is equal to g m1 m2. So further, to make this stand alone, you divide all through by m1 m2. So this is going to give us g is equal to f r square all over m1 m2. So that is what you get in that situation. So the next thing is can now bring in the dimensions of all of these, that is, put in their units and see what it will give you, how it will actually give you the units of we can see this clearly. Let me adjust this. Okay, so the unit of f, So we're going to put in, so I'm interested in the unit of G, so I'll put in the unit of F. Just replace each term with their unit. Unit of F is Newton. Okay, unit of force, F is a force, Newton, force of attraction. So we don't know what that one is. Newton is not in terms of our fundamental units. Don't forget our fundamental units. We have mass, length, and time. Okay, those are the three commonest. And mass is measured in kilogram, length is measured in meter, and time is measured in second in their SI units. So in this case, we have Newton, which is not one of these. So we're still going to have to simplify this, but just leave it the way it is now. And we have R. So I've been told that R is a distance. Distance is a length dimension. So I can replace this with meter. So I'll put that meter, then I'll square it, just like I have R square here, divided by M1. So my M1 represents a mass, and mass is measured in kilogram. So I'm going to put in kilogram here. Then I have multiplied by M2. M2 is also representing a mass. So the unit of mass is kilogram. So I'm going to put here also kilogram. So that's what I have here. Then I need to simplify Newton. So I think we did this before. We got the dimension of Newton, if you can remember. In case you cannot remember, we said that will be given by the relationship force is equal to mass times acceleration, and we said that from here you would see this is what you get from Newton's second law, and from here you would see that mass is measured in kilogram and multiplied by acceleration. Acceleration is measured in meters per second square. Okay, so the unit of force, okay, is equivalent to kilogram meters per second square. So Newton, okay, which we usually call the unit of force, is actually equivalent to this. So wherever you have Newton, you can replace it with kilogram meters per second square based on this relationship. Okay, so from here we're going to now use this, okay, instead of this. Why are we doing this? The reason we are doing this is we want to have only the fundamental quantities, okay, or the fundamental units here. That's what we mean by dimension. We want to get the unit of that quantity in terms of the fundamental units. Okay, so now we have Newton, okay, which is a derived unit in terms of the fundamental units, kilogram, meter, and second. So we will now put this in here instead of the Newton. So that is going to give us kilogram multiplied by meters per second squared multiplied by meter square. What I have done here is to just remove this n and put in this one because they are the same. Okay, so from here you're going to have divided by kilogram multiplied by another kilogram. That's what we have here. So this kilogram, we cancel this kilogram. Then I have here in the numerator, I have meter multiplied by meter square. That's going to be meter cube. Okay, then I have kilogram here at the denominator, so I can move it to the numerator. When I do that, it's going to be kilogram raised to power minus 1. Okay, so the next thing is, why am I doing this? Why am I bringing this to the top? Is because I want to actually arrange all of them, okay, on a line, like on the numerator only. That is, I want to make the denominator just 1, and I want to arrange them in this order, MLT. It is not a rule, but that's just the way it appears in most literature. So it's just good that we put it the standard way. Okay, so that's why I'm putting kilogram raised to power minus 1 first. Then I have meter multiplied by meter square. That's going to be meter cube. Then I have second multiplied by minus 2, so I have second square. Alright, so that is all that I have here. So that means if I want to the dimension of G, if I want to write it in terms of the fundamental quantities, not in this case, it is in terms of the fundamental units. If I want to write them in terms of the fundamental quantities, it's going to be in terms of M, L, and C. So kilogram is representing mass, it is the unit of mass. So I'm going to say this is equal to M raised to power minus 1. Meter is the unit of length, so this is standing in place for length. So this is going to be L to power 3. Then I have second is standing in place of time, So this is t raised to power minus 2. So that's that about that. That's the dimension of the universal gravitational constant. So I hope you get that. Alright, so the next one is, we said that we can actually use this dimensional analysis to evaluate or to find out if a particular equation is correct or is right or wrong. So, and how we do that is we look at the terms that have been added in that equation. So we have this assignment from the last class that you should find out which of this is correct. Okay, so and you're just going to do a dimensional analysis to find out whether or not it is correct. Okay, the dimensional analysis does not, like, you cannot use just dimensional analysis to conclude that the formula is correct. Okay, but you can use it to establish that the formula is not correct. That is, if it is not dimensionally consistent, that is, if the terms you are adding together do not have the same unit, then the formula is not correct. What I mean by that is this: you know that if you want to add something, let's say you want to add, let's say 2 kilogram, okay, we want to add it to another 3 kilogram. This is quite straightforward. We know this is going to be just 5 kilogram. Now imagine you want to add 2, let's say 5 kilogram. You want to add it to 2 meters. You know, this does not make sense. That means you're trying to add a different quantity. You're trying to add 2 different quantities. This one is a mass. This one is a length. So you cannot add them and, you know, just write out. I mean, in fact, physically this does not make any sense. So that is just the idea we're trying to say, that if you have an equation like s equal to ut plus half at square, okay, before you can add this and this, each one of them has to have the same unit. So that's what we mean by dimensionally consistent. That is, they have to have the same dimension. So the dimension of this must be the same thing as the dimension of this, which will definitely be the same thing as the dimension of this. Just like we had it here, the dimension of this was the same as the dimension of this, which is definitely going to be the dimension of this. So this is what we mean by additive terms. So the terms you are adding together in that particular equation must have the same dimensions for you to say that, okay, the equation is dimensionally consistent. And that would suggest that suggest that, okay, not establish that. We suggest that the equation is probably correct. Okay, so now look at the options we were given. We have v square is equal to u square plus 2a. So you have been told that v is final velocity, u is initial velocity, a is acceleration. So you want to find out if this equation is correct. So what you simply do is find out what is the dimension of this, what is the dimension of this, and what is the dimension of this. So if they have the same, if they all have the same dimension, then the equation is dimensionally consistent, or we say it is dimensionally correct. Okay, so v is a velocity. The unit of velocity is meters per second. I hope you know that. So this is meters per second. Alright, so v squared is going to be meters per second all squared is equal to, I have u squared. U is initial velocity. You know, this one is final velocity, this is initial velocity. Whether it is final velocity or initial velocity, they will have the same units. Okay, so if final velocity is 2 meters per second, for instance, and initial velocity is 0.5 meters per second, they still have the same unit. So it is the units we're interested in here. Okay, so this is also going to be meters per second all squared. Then we have this one, the unit of this one. I told you 2, or any constant that you have like this, like 1 over 2, 2, 3, or anything that is multiplying a term, does not affect the unit of the term. So it is only a that we're interested in here. Okay, so a is acceleration, and the unit of acceleration is meters per second square. Obviously, when you open this bracket, you're going to have meters square per second square. Here you're going to have meters square per second square. Whereas in this case, you're going to have meters per second square. So you can already see that the dimension of this, which is mt to power minus 2, is not the same thing as the dimension of this and this. Whereas these ones are m square t to power minus 2. M square, sorry. meter is length, this is L, and this is L square. So this is L square t to power minus 2. So as you can see now, they are not the same. This is the same as this, but not the same as this. So which means this equation is not correct. So that is how you tell. It's like you want to add something that is in meters per second, meter square per second square to another parameter or quantity that is in meters per second square. That does not make sense. So it is not possible. It's not the correct equation. So we consider another option. The other option says v square is equal to u square plus as. Okay, so we want to test for that also. So let's see what it gives us if we test for that and what we test for that. So we want to find out what we're going to get for v square is equal to u square plus as. So we're going to find out the dimension of each one of them. So what is the dimension of v? Dimension v is in meters per second, so I have v square is equal to, at this end also, this is initial velocity like we had it before. This is going to be meters per second all squared plus a is acceleration due to gravity, and a is acceleration, and acceleration is measured in meters per second square. Okay, multiplied by s is distance covered. Okay, so s is measured in meters. So with this, when you open this bracket, this is going to be meter square s to power minus 2 is equal to meter square s to power minus 2, and this one is also, this meter is going to multiply this meter, so you are going to have meter squared s to power minus 2. So obviously they all have the same dimensions. Okay, so that means this equation is dimensionally consistent, or you say it is dimensionally homogeneous. It does not mean the equation is correct or wrong. Okay, that means we cannot tell from dimensional analysis whether or not this equation is correct. Okay, but if we are to judge strictly based on dimensional analysis, we say this equation is correct. Of course, the proper equation should be v square is equal to u square plus 2as. So now this 2 is not present here. Yes, dimensional analysis cannot tell whether or not this is not correct the way it is. So it is not a sufficient means of establishing whether or not an equation is correct, but it's just a way to tell if we can, to see if we can tell that an equation is not correct because the dimensions are not consistent. So when the dimensions are consistent, we cannot tell. There has to be other factors considered before we can conclude that the equation is correct, but we can conclude whether or not it is dimensionally consistent. Okay, so that's that. So what's the next one? Now we have the next option. V square is equal to u square plus 2s. Obviously you're going to have v square is equal to u square plus 2s. So if you have this, when you consider this is still going to be meter square per second squared. Okay, it's equal to, when you do this also, meter squared per second square, just like we had it here. Then when you do this one, the 2 is unitless, is a constant. S is distance, it is measured in meters. So can you see now, you have this meter square per second square, meter square per second square, whereas this one is meter. So that tells you that the equation is not dimensionally consistent. I mean, this equation is not dimensionally consistent, so it is not correct. Okay, so I guess that is that about that. You know the answer now, so the answer will be here in this case, because as far as you can establish using dimensional analysis, this is the only equation that is dimensionally consistent or dimensionally correct amongst the options you've been given. Alright, so I guess that's that about that. Then let me see the next one. We also talk about energy, just like you have it in the slide, that you should establish the dimension of energy and the dimension of potential. So let's quickly look at them. You were even supplied with the formula that the energy is given by mv square. Okay, just like kinetic energy is half mv square, but that half does not make any difference. You know, half is simply unitless, 1 over 2 is unitless, 1 over 2 is a scalar, just a constant. Okay, so let's look at the dimension of energy. So I thought that E is equal to mv square, okay, where m is the mass, okay, and v is velocity or the speed, as you may like it. So if I want to get the dimension of E, I'm going to replace each one of them with their units. Okay, so as far as I can go using the fundamental units of kilogram, meter, and second. So in this case, mass is here and it is measured in kilograms, so I replace it with its unit, kilogram. V is a velocity, so I'll replace it with its unit, which is meters per second. Then I'll put the square as is required. So from here, this is going to be equal to kilogram meter square. You know, when I open this bracket, this is going to be meter square, and I'm going to have second square. So that means now in terms of the fundamental quantities, no, this is in terms of the fundamental units. So in terms of the fundamental quantities, the dimension of energy will be, you know, kilogram representing m, okay, meter representing length squared, second representing time to power minus 2. So that is the dimension of energy. And although this has been used to calculate the dimension for some form of energy, it actually applies to any form of energy. So any form of energy you can think of actually has this dimension, okay, whether it is thermal energy, whether it is electrical energy, or whatever, they all have this they all have this dimension. Okay, so the next one is potential. Okay, so in this case you have something like power. Okay, you know, power is rate of expenditure of energy. Power is energy over time, so that's exactly what you have here as potential, being called potential. So it is actually power. All right, so power is mv square over t. That's like energy over time, knowing that energy is mv square. All right, so from here we're going to have something like this. Okay, I'm calling it power, so I'm saying that power is starting afresh here. Power is equal to mv square all over time. So with this we can now get the dimension of power. Dimension of power is equal to, I replace all the quantities here with their units. So m is measured in kilogram, put it here. V is the velocity, it is measured in meters per second, put it here and square it. T is time, which is measured in seconds. Okay, so at the end of the day I'm going to have this as kilogram. You know, I said we should always have this arrangement, MLT kind of, so that's why I'm putting the kilogram first. Then L is measured in, that's length, it is measured in meter. So the next M I have, I'm going to put here M. So M is the next thing I'm putting here. Then I have S raised to power minus 1 all square. That's S raised to power minus 2. Okay, then I have another S at the denominator. That's like multiplying this by S raised to power minus 1. I hope you understand that from indices. Okay, so from here this is going to be the dimension of P. In terms of the fundamental units, let's conclude that it's going to be kilogram meters per second to minus 3. You know, this is minus 2 plus minus 1, which is minus 3. Sorry, m here is going to be squared also, so this is going to be m squared. Alright, so this is m squared. Alright, so from here I can now write the units of this, or the dimension of this, in terms of the fundamental quantities. So I know that kilogram is representing mass, so I'm going to put m, which is m to power 1. Then I'm going to put, for meter, I know meter is representing length, so I'm going to put L to power 2. And for the second, I know second is representing time, so I'm going to put C to power minus 3. So I have this as the answer for the dimension of potential, or dimension of power, as you may like to call it. Alright, so I guess that is that. about that as far as this portion is concerned, or this topic is concerned. So try and get more questions on this. I think maybe I can get a textbook that you can read. Please, and please, it is very, very important that you actually understand these things. That is the appropriate thing. That's the appropriate thing. Just try and understand them. So we are done with that slide like that. So let's move to the next one, lesson 2. So lesson 2 talks about scientific notation, powers of 10, multiple and submultiples. So you will also come across this, so it's better we address it now, so that when you come across them you will not find them difficult. Okay, no, we're going to solve all the problems, any kind of problems you may encounter. We're going to solve them together. So I just have to follow a proper process so that you understand these things properly. That is the best for both of us. Please, that is the best for both of us. Alright, so look at this powers of 10. If you have powers of 10, how do you deal with them? You know, there are times that when you carry out your calculation, for instance, if you are calculating whatever it may be now, you may be calculating and you get an answer like 0.000123. Okay, you know, it may even be more than that. This is approximately 0, but there are instances where you don't even want to approximate to 0. You want to put down the number as small as they may be. You just want to put it down like that, so that you know, it actually makes sense in that context. Okay, so to do this, to make it compact, that is to save space, sort of, we can actually write this in what we call the standard form. That is by writing it as a multiple of 10. So what we simply do is we write it in the form a times 10 raised to the power b. Okay, where a and b, where a is a number between 1 and 10. That is a number between 1 and 10. A number, so a is usually a number between 1 and 10, so it is less than 10, it is not up to 10. So you have a number between 1 and 10, so it can be 1 but it cannot be 10. Alright, so in this case, what you simply do is move the decimal places forward. 1, 2, 3, 4, 5. So you have, in this case, I'm going to write this as 1.23. So why did I stop there? Because I have now achieved this objective. I've made it such that the number I will have to write first is a number that lies between 1 and 10. It cannot be up to 10, but it can be exactly 1. Alright, it can't be less than 1. So I've gotten that here, and for me to get that, I had to move my decimal places forward 5 times. So that is going to give me minus 5 here. If I had to move my decimal places backward, I mean to the left side, then this will be a positive power. If I have to move my decimal places to the right side, this will be a negative power. So I guess that is that about that. So you have situations, or you may come across situations where you are told to write your answer in standard form or produce your answer in standard form. So this is how to put the answer in standard form. So for instance, if you have something like 8,900, okay, let's say, or something like 89,000, and it's taking too much time, or say 890,000, it's taking too much space now, you can put it in standard form. So what you do is, you know, this is like 890,000.00, so or 0.0. So you move, in this case, you move the decimal places, you know, to the left. So you're going 1, 2, 3, 4 5. Okay, so you have to move it 5 times to the left before you arrive at a number that lies between 1 and 10, which is less than 10. So this is going to give us 8.90 multiplied by 10 raised to power, we have to move it 1 2 3 4 5, so 10 raised to power 5 in this case. I told you, when you have to move to the left like this, you're going to get a positive power for 10. If you decide to move to the right, you're going to get a negative power for 10. Alright, so that is how to put your numbers in standard form or results in standard form. Also, now when you have answers like this, when you have multiples of 10 multiplying a result, okay, there are some what do you call it now? There are some prefixes that we usually attach to the quantity to depict that. Okay, for instance, you've heard of kilobytes, megabytes, terabytes, gigabytes, and all of that before. They are actually used to quantify the power of 10, okay, that is attached to that particular number. For instance, if I say that I have 2 gigabytes, okay, I'll say 2 megabytes, kilobytes, whatever. Giga is actually a prefix, okay, prefix. This is actually gigabyte, and giga is a prefix to byte. Okay, byte is the root word here. Alright, so giga itself has a meaning. So I can actually have something like giganewton, I can have something like gigameter, I can have something like giga ampere or anything. So it's just a prefix to denote the power of 10, okay, with which this is multiplied. So what you have here is actually 2 times 10 raised to power. So giga is actually 10 raised to power 9. Okay, when you come across giga, so this is actually 2 times 10 raised to power 9 bytes. Okay, that's what I have here. So this giga and other prefixes you may come across are usually used to denote the power of 10 with which that number is multiplied. So for instance, if I talk about 1 kilobyte, when I say 1 kilobyte, it is simply 10 raised to power 3 bytes. If I say 1 kilogram, it is simply 10 raised to power 3, which is 1000 gram. Okay, if I say 1 megabyte is simply 10 raised to power 6 bytes. Alright, so that's the way it works. So these are the prefixes. You have them in this slide, so you should know them offhand. I don't think you need to cram any of them. When you actually use them in problem solutions, like you solve a lot of problems that involve using them, you will definitely naturally retain them. Okay, for instance, you can have deca is 10 raised to power 1. You can have Eto is 10 raised to power 2, kilo is 10 raised to power 3, mega is 10 raised to power 6, giga is 10 raised to power 9, tera is 10 raised to power 15, beta is 10 raised to power, tera is 10 raised to power 12, and so on and so forth. So you can check that in your slide. We also have those that are negative powers. For instance, deci is 10 raised to power minus 1, centi is 10 raised to power minus 2. For instance, when you hear something like 1 centimeter, it simply means 1 times 10 raised to power minus 2 meters. Okay, so that's how to deal with all of that. So you should, I guess that is the only one here that may give you some issues. So that's if you don't already know them. So that is that about that. So let's start about this second slide. Alright, so we can begin to discuss So we can begin to discuss dynamics. Okay, so we can discuss dynamics. So we begin with the first law of dynamics.